Today we are going to start study the lock-free data structures. So in the previous videos we studied how concurrent data structures may improve the scalability when compared to sequential data structures protected by locks. And as an example, we studied lock-coupled linked list. And from now on, we are going to focus on what is called lock-free data structures. So the dictionary meaning of this lock-free is there is no locks. The data structure is not protected by locks, but it has further meanings that will be defined later, which is very technical. So I will going to introduce the concept of these lock-free data structures and a few representative examples of lock-free data structures. So in this semester, in 2020 fall, the homework 5 will be about implementing what is called split ordered list, that is basically a hash table. And homework 6 will be implementing a garbage collector for lock-free data structures. So as a result, you are going to be able to implement on your own the lock-free data structures, especially the most important one, hash table. Okay, so far so good. And let's think about locks. What is lock? Lock is allowing only one thread to access the shared data. And as a result, the other threads may pause or stall. So if one thread is holding a lock and then do expensive computations or I/O, or even it may crash and it doesn't return at all, then maybe it is possible that the thread is paused or stalled. And in that case, the other threads cannot acquire the lock and it cannot proceed on its operations. So as a result, it may be possible that the deadlock may happen. The deadlock is that the threads are holding resources that cannot, that makes the progress impossible. For example, if thread A is holding the lock L1 and it is trying to acquire L2, and also let's assume that thread B is holding lock 2 and it is trying to acquire the lock L1. And in this case, both A and B, they cannot proceed on each operations because A cannot acquire L2 because L2 is already acquired by B, and B cannot acquire L1 because L1 is already acquired by A. And as a result, there is a deadlock. They cannot proceed at all. And it is usually happening in lock-full concurrent programming. So in order to do so, we may need to somehow manage not to incur such situations. And one of the countermeasures is that even if deadlock happens, it may be possible that we can detect deadlock and kill one of the operations. For example, B is holding L2 and this is deadlock, and as a result, we may pick B as a victim and just throw away B's operations. And then L2 will be freed, and then A will be able to acquire the lock L2, and it can proceed. And as a result, as a whole system, it guarantees some progresses. At least A will progress. It may be possible that we can kill A and let B progress. In either way, we can make sure the system as a whole progresses. It is a countermeasure, but it is not very perfect because there is a situation that is called live lock. So see the contrast between deadlock and live lock. So it actually does something, but it is killing the operations. So let's see that B1 is trying to acquire the lock L1, L2, and then L3. B is acquiring L2, L3, and then L1. C is acquiring L3, L1, and L2. So if B just acquired L2, and the C is holding L3 and L1, so they progressed. They acquired the lock L2, L3, and L1. And if it is the case, it is guaranteed that no thread is able to progress because all the locks are held and all the threads needs to acquire more locks. And as a result, we may kill C because it is a deadlock. So we want to kill one of the operations. And at this point of time, we want to kill C because it is just for random reasons. And after that, let A acquire the L1 and B acquire an L2 and L3. So B already held L2, and let's say that B additionally acquires L3. And it's almost the same situation has happened. One thread has acquired one lock, and a thread has acquired two locks. And as a result, we may detect a deadlock for the same reason as above, and we may kill B. And the same thing may happen. Let's C acquire a lock, and then A acquire an additional lock, and then A is killed. And it can loop. After A is killed, it may be possible that we have to kill C, and then B, A, C, B, A, C, B, A, etc. So if that happens, they seems like progressing because some operations are killed, and the other operations are making more progresses. But at the end of the day, if we look at the entire execution, no threads are making meaningful progress because they are kept killed by the deadlock detector. So this is a problem. This is the problem that is due to locks because lock disallows the other threads accesses at all, and as a result, it may be possible that no threads can progress. Even though we can deal with the deadlock with the operation stopping the operations, the LiveRock problem may happen. So it is much more complicated than what it first looked. So this kind of situations is the enemies of the lock freedom. So lock freedom is basically trying to avoid such situations altogether. We want to make sure that at least one of the operations are going to progress. So that is the meaning of the lock freedom. So the lock freedom as a technical term is not only meaning the lack of the locks, but also meaning the progress guarantee. So at least one operation should progress. And if you use lock, it is almost always the case that it is not lock free. So it is like euphorism. It looks like euphorism, but euphorism. 말장난처럼 보이겠지만, so it is actually not. So if you have lock, it is lock freedom. Even though you don't use lock, it may be possible that it is not lock freedom. So in order to guarantee such a progress guarantee, we have to give more attention than just not using locks. So from the next slide, I'm going to explain how to concretely achieve this lock freedom for concrete examples. So the key idea here is that we want to make sure that the operations progress at a single point, which is called a commit point. So suppose that we want to design a stack, and we want to design push and pop operations for the stack. And we make sure that, for this idea, we make sure that a single instruction, single architecture instruction is committing the changes to the data structure. And by doing so, we can leverage architecture's guarantee of progresses. So architecture, hardware, guarantees that if there are multiple CPUs cores and there are multiple threads, then at least one of these threads or cores are able to execute the following instruction. And also, if the following instruction is, for example, RMW instruction that has success and failure, then the architecture or hardware guarantees that at least one of the cores will succeed in the following, the RMW instruction. So it is guaranteed. So it is a kind of progress guarantee. The architecture guarantees the progress of the RMW instructions. So by leveraging the architecture guarantee, we can design a lock-free software. So by using a single RMW instruction as a commit point, we can say that, oh, even though multiple threads are trying to access the stack at the same time, some are pushing and some are popping, at least one of the operations will succeed because one of their RMW instructions will succeed. So okay, that is basically what's the high-level key idea of almost all lock-free data structures, and it usually should be the read, modify, write operations, because read is impossible because read doesn't change the memory state at all. So it is not acting as a commit point, and also write is limited. It is almost impossible to achieve the commit point using write instructions because write. If you write a value, it can be overwritten arbitrarily. So there's not so many are guaranteed by the write instructions. So that's the reason why writes are usually, almost always, not able to be used as a commit point. So actually, RMW instruction is introduced in the history in order to guarantee the single instruction commit point, in order to support the single instruction commit point. So in 1970s or so, in the mainframe computers, the RMW instructions are introduced in order to achieve such synchronization among multiple threads or multiple cores. Okay, so and this single instruction commit point idea is indeed defeating the enemies of lock freedom, because thread pauser still doesn't bother with a single instruction. So single instruction is always executed or not. It is not paused. It is not interrupted at all. Instruction is atomic. It is either completely executed or completely not executed. So there's no way for the other threads to interrupt or interfere with the single instruction. And also, roughly speaking, because there's no locks, we don't have deadlock and live lock problems. So if we design this single instruction commit point well, then we can guarantee that there will be no deadlock or no live lock problems, because at least one of the operations will be going to be successful. Okay, and as a side benefit or side effect, you can additionally achieve scalability, because unlike locks, the contention among multiple threads are happening only at a single instruction. If you use protect data structure with a lock, then you're going to execute multiple instructions inside the lock. And when the multiple instructions are executed, the other instructions, other threads or other cores will not be able to proceed. But on the other hand, in the lock-free data structures, using single instruction commit point, we can effectively reduce the contention to just a single instruction, because the other instructions are just preparing for the commit or the post-commit cleanup, and they are not contended at all. The contention among multiple threads are only happening at a single instruction, and that is basically the reason why we can achieve better scalability by using this idea. Okay, so let's see how this can be implemented in the following example, which is the Treiber stack. Treiber stack is one of the earliest concurrent lock-free data structure, and this is published as an internal document of a company. And you can see the source code here. So in this repository, you can see the entire source code of the stack. And the Treiber stack is basically a singly linked list. So it is a linked list, and the head pointer is basically the stack top. So this is an illustration of such a stack. So top, there is the top pointer, head pointer is the top, and the values are stored in the stack, and there is a null pointer here. And when you push a value, you're going to insert here. When you pop a value, you're going to pop a value at the top of the list. So by doing so, you can effectively guarantee that, oh, this will be actually a stack, pushing and popping at one end, or first in, first out. By the way, do you know how to pronunciate FIFO? It is actually FIFO, not FIFO. So if you are going to pronunciate it in front of the others, try to remember it is FIFO, not FIFO. Okay, so now let's explain how to pop a value from this linked list. So suppose that thread A is trying to pop a value from the top. How to do it? It first reads the top pointer. So this is a pointer to the next block. So we are going to read it. So it is the beginning of the pop operation. And the second thing to do is read the next pointer. The reason is that we are going to remove this 42 node, and the new top should become pointing to this 37. And as a result, we need to read this pointer. And the next step is performing a compare and swap from top. So this is a pointer that was originally pointing to 42, and you have to perform a CAS from 42 to 37. As a result, the top is now pointing to 37, if successful. And after that, you can return 42, because you effectively changed the stack state from 42, 37, 666 to 37 and 666. So you just popped the first value 42 at this step. By casting from 42 to 37, 42 is removed from the stack. So you can successfully return the 42. If the previous cast was a failure, you didn't succeed in performing this cast, and then you can just go to the beginning and do it again. Because if the cast is unsuccessful, that it means that the top pointer has already been changed by the other threads, so you need to start again by reading the top pointer. Now, let's suppose that another thread B is trying to push a value to the stack. The first thing to do is reading the top pointer, which is pointing to, for example, 37. And now, you create a new node. You create a new node that is containing the pushed value, and the next pointer of this node should point to the original top pointer's value, which is 37 in this case, because you read top pointer and it was pointing to 37, and that's the reason why we are pointing to 37 in this new node. And furthermore, we are performing a CAS from the top for the top pointer from 37 to the new node. So by doing so, we can effectively inserting a new value. If successful, if the CAS is successful, the content of the stack is new 37 and 666. That is effectively the original stack that is inserted by the new value. Okay, so by doing so, we can manipulate a singly linked list in a synchronized manner among multiple threads, and this push and pop synchronizes with the CAS operation, the compare and swap operation on the top locations. So if this pop succeeds in the performing a CAS, then all the concurrent operations will fail to perform a CAS on this top location. And as a result, it is as if the other threads are executing the operations after thread A's pop operation. If B succeeds in its operation, so it is successfully performing a CAS, and as a result, all the concurrent operations will be able to perform its operations after B successfully pushed the value. And here, this CAS is the single instruction commit point that we discussed just before in the previous slide. If this is successful, the entire operation is successful. If this CAS is successful, then the entire operation is successful. Otherwise, they are not successful. So this is the single instruction that decides whether an operation is succeeded or not. Okay, so far so good. So from now on, we are going to look at the code and then go back to this slide and explain a little bit more about the synchronization. So now let's look at the code. So this is the code of the stack that is in the repository, the courses repository. And as I said, it is a singly linked list, so you need to have a head pointer. Head pointer is pointing to a node here. And from now on, for lock-free programming, we are going to use what is called the crossbeam epoch library, which provides a few utilities to implement lock-free concurrent data structures. So let's say that atomic is just a pointer. You can think of this as a pointer to node T. And atomic means that it is a special pointer on which you can perform atomic operations like compare and swap and atomic reads and writes. So this is the intentionally racy location. You are implicitly assuming that multiple threads are accessing the head pointer at the same time. And it is safe only if it is marked as an atomic. So this is pointed. This has a head pointer to the node, and each node has a value. And the next pointer. The next pointer is the same with the head pointer, and the data is wrapped with what is called a manually drop. So I'm going to explain what's the meaning of the manually drop later. So you can just think of it as T for now. It is containing the data of type T. So at the beginning, the empty stack is just having a null pointer. So head pointer is null for the empty stack. This is very much anticipated because the stack values are what is in the linked list, and the empty stack should have no value at all. Now, let's suppose that we want to push a value. As I explained in the figure, you first create a new node here. So this is the node, and you can think of it as an allocation in the heap. So in the heap, a new node is allocated. But in order to use the crossbeam epoch library, you need to use what is called owned rather than box or other types. And let's think of it as just a heap allocation that is meant to be used for concurrent data structures. And the data will be the new value given here. And the next pointer is yet null. Okay, so far so good. And now we are going to create a guard for the concurrent data structure operation. So we are going to study the meaning of this pin and guard later. But for now, let's assume that in all data structure operations, you are going to create a guard. So this is related to the garbage collection of data structure. And for now, let's ignore it. So at the last part of this lecture, last part of this semester, we are going to deal with the garbage collection, and at that time we are going to study guard and pin and the purpose of this course beam epoch library. For now, let's just assume that at the beginning of an operation, we are going to just acquire a guard here like this. And as I said before, in order to push a value, you'll first read a head pointer. You read the head pointer, and then the new node's next pointer becomes the head pointer. So effectively, you are trying to insert a value that like this. Sorry. Oh. My Firefox is okay. My Firefox was gone and it is restarted, so oh. Sorry, I will configure this a little bit. Okay, so, okay, we are back. Okay, we are going to insert a new node, which is going to point to the original head like this. And then we are going to perform a compare and swap. Compare and set and compare and swap, they are the same. We are changing the head pointer from the original head to the new node atomically. And if it is successful, we are done. We just return. And if it is unsuccessful, then we are going to start again and try again. So the reason why we do this is that after failing to perform the CAS, the new node here is returned here, and we have to set the n here again by the what is returned from the compare and swap. So far so good. And let's see what's going on in the pop operation. So in the pop operation, you are going to make a guard again, and then read the head pointer. And you are going to dereference the head pointer because you are going to read the next pointer of the head pointer. So you are dereferencing, and if it's a null pointer, then you're going to just return null, none. It means that if the head pointer is null, then it means that there is no value inside the step. That's the reason why we return immediately none. If it contains something, then you're going to dereference the next pointer of the head pointer. And now we are going to perform a compare and swap by atomically changing the head pointer from the original head to the head's next pointer, which is right here. So far so good. And if this compare and swap is successful, then we know that we succeeded in the pop operation. So we are going to return some value. And what we are going to do is that we first read the head pointer here. The head pointer's data is right here. And then we are going to mark the head node as no longer used. So we are going to destroy this head pointer using this API. This is a little bit different from the free because it is not going to deallocate this node immediately, but it will wait for a few more times before actually deallocating this head pointer. it is also related to the garbage collection. And the reason why this should be delayed is that it may be possible that the other threads are concurrently accessing the head node at the same time. So we have to wait for the other threads to finish accessing the head node. And only after that we can destroy this head node using this API. So we're going to study this API a little bit more at the later stage of this class. And for now, let's assume that you can defer destroy a node only after you detach the node from the data structure completely. So here we perform the compare and swap. So the head pointer was in the head, but this head value is completely eradicated in the memory by this compare and swap operation. Because now the new head is next and the old head is no longer present in the memory. And only after that you can do this defer destroy the head. So this is the API contract between the Crispim epoch and your stack code. And please memorize the contract. You have to remove all the reference to the pointer before you actually call defer destroy. So far so good. And you can also check whether the value the stack is empty by looking at the head pointer, etc. So that's basically what's going on in the stack implementation. And now let's look at what's going on in the stack in more details. So in particular, we want to study the synchronization that is happening inside the Treiber stack. So my slide is also closed, so I'm going to Okay, so please wait for me a little bit more. Okay, so now we are back in the slides. So I have a few questions. That is, at the line 50 we are using release, and also at the line 64 we are using acquire. Why we do that? Why we do that is the question. So that is basically related to the relaxed behaviors and the promising semantics, and why we have to do release and acquire like this. So I'm going to explain this using by going back to the code here. Okay. Oh. Okay, so we are back in the code here. At line 50, we are using release. At line 64, we are loading acquire. So the reason why we do release acquire here is that we want to release the value. So if you push a value to the stack and then pop the value, we hope that there is a synchronization between the push and the pop. So it is just like message passing. If thread A pushes a value and then thread B pops the same value, then it should be the case that all the knowledge that has been gathered so far by A must be transferred to thread B. So as a result, so we want to guarantee something like this. If A is, for example, writing a value and then push a value, to the stack. We want to make sure that the access value is 42 here. So the code is like this. If you write the value and then push a signal to the stack, and in thread B, it is receiving the signal, and at this point of time, we want to make sure that thread B should be able to see the value x equals 42. Actually, it must see the value x equals 42. So in order to do so, there should be some release-acquire synchronization between the push and pop. That's the reason why this is release and this is acquire. The head pointer is changed using release ordering. And at the pop, you have to acquire this in order to transfer the view on the value x, for example, to the thread B. So access view, x equals 42 view, is transferred to the head pointer by the release instruction at this point of time. And it is acquired here, and as a result, x must be 42 at this point of time. So that's the reason why we are going to use release and acquire for these lines of code. And furthermore, another question on this tag is that we are using what is called manually drop. So what's the meaning of this manually drop? And actually, this little bit complicates the code like this. So in order to read the data, in order to return a value in pop, we are reading the internal value that is inside this manually drop. And furthermore, we are creating a new node using this API of manually drop. So it is a little bit complicating what's going on there. So the reason why we do this complication is that when this node is destroyed at some later point of time, we don't want to call the destructor or drop of the data once again. The data is already taken and it is returned to the pop function as a return. So the data, the same data, must be deallocated without incurring, without calling the destructor or drop. So that's the reason why it is marked as manually drop. If it is marked as manually drop, when the head node is destroyed or deallocated at some point of time later using this API, then you can guarantee that you are not going to call the destructor again because the destructor will be called by the caller of this pop. This guard default destroy should not invoke the destructor. So it is guaranteed by this manually drop. If the data is wrapped with the manually drop, its destructor is not invoked in this node. So that is basically the meaning of the manually drop. So far so good. And let's go back to the slides. And yeah, it should be release and acquire in order to achieve the synchronization between push and pop. And this should be satisfied by almost all the concurrent data structures. If you push a value and pop the value in queue, then there should be some synchronization, etc., etc. And that's the reason why some orderings must be marked as release and acquire. Another question was manually drop, and as I said, we need to mark some data with manually drop in order to make sure that the destructor will not be called for data when the node is later deallocated after the value is returned. So it is very common in log-free data structures because even though you return the value, your node must be there for a little bit longer time. And in order to do so, we need to mark the data as manually drop. So Q also wrap data with manually drop. Hash tables also wrap the data with manually drop, etc., etc. So that is basically the meaning of this manually drop. There are a little bit more questions, and I hope that you are going to study this kind of this slide on your own as a homework. And in terms of the promising semantics, the invariant of the stack is that the head pointer value has a release view. So recall that all the messages in the promising semantics has a release view. And the invariant is that the head pointer, its release view is bigger than or equal to all the messages for all the nodes, value and next pointer. So you write values, you write next pointers for a particular nodes, and there are multiple nodes. And the invariant that is maintained by the operations is that at any given time, head pointer's value's release view is bigger than or equal to subsumes all the nodes value or next pointer's messages. So this release and acquire is actually guaranteeing that. Release is maintaining the invariant, and acquire in the pop operations is explaining the invariant so that the push and pop are properly synchronized. So this is a little bit difficult topic, so I will not ask these in the exam, but if you're interested, please read this paragraph and ask questions if you are more interested. Okay, so far so good. So far we studied the Treiber stack. So Treiber stack is one of the most basic and yet interesting data structure, concurrent data structure. And from the next lecture, we are going to study queues or other data structures that is a little bit more complicated than the stack. And as a homework, you are required to implement what is called split ordered linked list, which is meant to be a hash table, concurrent hash table.